Hello, my name is Steve. Welcome to my YouTube channel. In this video, I'll talk about the second part of the Chapter 1, Introduction to Differentiation. In the second part, it's about finding the derivative from the first principle. This video is all about this limit. The limit of the function fx plus h minus the function fx divided by h when h goes to 0. In order to explain this limit, we try to explain the ratio without the limit. The ratio just fx plus h minus fx divided by h from a secant of a curve. Okay? When we have a curve, we are choosing one point. So here would be at x. Okay, so here would be y. So here x. You're choosing one point from here, another point from here. If the difference from this point to this point is h, then this point would be x plus h, right? Okay, here's the value for the x at these 2 points. And the value for y of the function at here would be fx. At here would be the fx plus h. Okay? Let's form a right angle triangle over here. Okay? We have a right angle triangle here. When we talk about, okay, this one, fx plus h minus fx. So this point fx plus h minus fx would be the difference of here. So actually it's over here. So this one would be fx plus h minus fx. Or we can say the delta y. Delta y. Okay? H will be the difference of these two ends. So here will be h. Or we can say x plus h minus x. So this one actually just h. Okay? Here we can say is delta x. Okay? So this ratio is the delta y divided by the delta x. Right? This one actually is the tangent of this secant. In this right angle triangle, right? The tangent, if this angle is alpha, so tan alpha equal to the delta y, the rise over the run, over the delta x. Right? So this one is the gradient of this secant. Okay? Without the limit, this ratio is the gradient of this secant. With the limit, when h goes to 0, which means this point goes to this x, right? Then this point will goes to this point as well. So eventually, these points will goes to this point. So the limit of this ratio would be the gradient of this point on the curve. So it would be one point only. Okay? Then, if we can find all the gradient of the curve for all the value of x, then we can get a gradient function of the original function. We call this gradient function as the derivative or a differentiation function of the original function. Okay? We'll try a simple example. Starting from the fx equal to x squared. Okay? So the limit when h goes to 0, fx plus h minus fx over h equal to the limit h goes to 0, fx plus h, then we replace the x with the x plus h, will become x plus h squared minus x squared. Right? Again, divided by h. Here, we have to expand the x plus h to become x squared plus 2xh plus h squared minus x squared divided by h. Then we can eliminate this x squared and this x squared. Here we have 1h, here we have h squared. Then we can factorize 1h outside to become limit h go to 0, factor out 1h, and then we still have 2x plus h divided by h. Here we can eliminate the h from the numerator and the denominator. The last step, we have the limit when h goes to 0, 2x plus h. When h goes to 0, this h goes to 0, right? This 2x, nothing changed. So the limit of this one would be 2x. Okay? This several step means finding the derivative of the function fx equal to x squared from the first principle using this limit. Okay? Using this limit. Okay, from the first set example, when the fx equal to x squared, then we have the fx dash equal to 2x. We can use fx dash to represent the derivative of the original function, or also we can use dy over dx. dy over dx, we can say the delta y over the delta x means the changing in y divided by the changing in x. Or also we can say we find the derivative of the function y with respect to x. Okay, so we can use this form or we can use this form, equal to 2x. When we're using y, then here y equals to x squared. Okay, or if you prefer using fx, so here we can say dfx divided by dx. We can use this form, or this form. They're all up to you. Okay. Okay, let's try another example. Let's try the function y equal to x cubed. Okay, let's find the derivative of this function from the first principle using this limit. Okay, when the function of this one, then the limit h goes to 0. The fx plus h means the x plus h to the power of 3 minus x cubed, right? And then divided by h. Okay, the next step we have to expand x plus h to the power of 3. Okay, will be x cubed plus 3x squared h plus 3x h squared plus h cubed, and then minus x cubed divided by h. Okay, x squared x cubed minus x cubed over here, we can cross out. This h squared and h cubed, we can factorize 1h out to become the limit. To become the limit, h goes to 0. H, we still have 3x squared plus 3x plus h plus h squared, and then divided by h. Okay, we can eliminate this h from the numerator and the denominator. Okay, next step. So here we still have 3x squared plus 3xh plus h squared. When h goes to 0, this part will become 0. These will become 0. So at the end, we have 3x squared. Okay? So here, 3x squared is the derivative of the function y equal to x cubed. So these steps we call finding the derivative of the function from the first principle, from this limit. Okay? Okay. The second example, where the function fx equal to x cubed, then is derivative equal to 3x squared. Okay, let's try another one. This one would be a little bit harder. Y equal to the square root of x. Okay, let's try using this first principle. The limit h goes to 0. So x will replace with x plus h minus the square root of x divided by h. Okay, so this limit using this one. Okay, next step, we have to times the x plus h plus f square root of x on the both sides. Okay, so the limit h goes to 0. This one, on the numerator, we are starting from a minus b times a plus b. From this formula, become a squared minus b squared. So here, when this one times this one, will become x, the square root of x plus h squared. So it will become square root of x plus h squared. So this one actually is equal to x plus h. Okay? So here would be x plus h minus x. And the numerator will be x plus h times the square root of x plus h plus square root of x. Okay, next step. The limit h goes to 0. X plus h minus x, we still have 1h on the top. Okay, divided by h times the square root of x plus h plus square root of x. Okay, h, we can eliminate the h from the numerator and denominator. Okay, next one. The limit h goes to 0, 1 over the square root of plus the square root of x plus h plus square root of x. When the h goes to 0, this one will become 0, right? And x nothing changed. So we have 1 over square root of x plus square root of x. Right? We can combine these two together to become 1 over 2 times square root of x. Or we can say we bring the 1 over 2 outside and then times 1 over square root of x. Right? Also, we can change a little bit the form. 1 on 2 times x to the power of negative 1 on 2. Because 1 over the square root of x equal to 1 over x to the power of half, right? Equal to x to the power of negative half. Okay, so eventually we find half times x to the power of negative half as the derivative of the function y equals to the square root of x from the first principle. Okay, from the third example, we have fx equal to square root of x. Then its derivative equal to half times x to the power of negative half. Okay. From these three examples, we can try to find the patterns of the way to finding the derivative of the function in this form: the x to the power to the power of 2, x to the power of 3, or x to the power. So square root of x actually is x to the power of half, right? If the function is y equal to x squared, then y dash would be equal to 2x 2 times x. If the function y equal to x cubed, and y dash would become 3x squared. If the function y equal to the square root of x, so this one actually is equal to x to the power of half, right? Then y dash will become half x to the power of negative half. Okay, try to find the patterns of these three samples. We have a 2 in front of the x as the coefficient of our function, 2, 3, half. So these 2 equal to this number, right? These 3 equal to this number. These half equal to this power, right? So actually this coefficient number is from the power of the x. Okay, so here x to the power of 1. So here from x to the power of 2 to x to the power of 1, from x to the power of 3 to x to the power of 2, from x to the power of half to x to the power of negative half. They all have one difference, right? So 2 minus 1 to become 1. 3 minus 1 become 2. Half minus 1 become negative half. Then we can summarize the pattern. If the function y equal to x to the power of n, then y dash would become this number from the power, right? From the power of the original function. Okay, we bring the n to the front. And then times x, the power would minus 1 to become this one. So we have n minus 1. Okay, this one actually is the formula for us to find the derivative of the function when the function in the form x to the power of n. Okay, the same thing we can using this formula to, for example, y equal to x to the power of 8. No difference to this one. So the y dash will become, bring the power to the front, 8. And then times x, the power will minus 1, 8 minus 1 will be 7. So when the function y equal to x to the power of 8, is the derivative will be 8 times x to the power of 7. Okay? Another one. If we have a y equal to x to the power of negative 2, for example, then y dash will become, bring the whole power. So here the power will be negative 2. So bring negative 2 to the front. And then times x. So here, negative 2 and then minus 1 will become negative 3, right? So here x is to the power of negative 3. So if the function is y equal to x to the power of negative 2, then its derivative will be negative 2 times x to the power of negative 3. Okay? As long as we can have the function y equal to x to the power of n, then its derivative of the function will be n times x to the power of n minus 1. Okay? So here is the first formula for us to find the derivative of the function in this form, y equal to x to the power of n. So what's the derivative of the function can tell us about the original function. I'll give you an example in the next part. Okay, for example, if the function is y equal to x squared, then its derivative would be 2x, right? So bring the power to the front. And the power minus 1 will become 1. So it will become 2 times x. Okay? Then here will be the graph for y equal to x to the power of 2. Y equal to x to the power of 2. Okay, is derivative function y dash equal to 2x. So when x equal to 0, y equal to 0. So we close this point. So 2x, this one actually is a straight line. When x equal to 1, y will become 2. Okay, we're crossing these 2 points. So this one will be y dash equal to 2x. Okay, what's the relationship between this function of this function? Okay, so the original function y equal to x squared, in this part, the left hand side, here is a decreasing function, right? In this part is the increasing function. To its derivative function, y dash equal to 2x, this part is actually a negative. All the value for this y dash is negative. In the right hand side over here, all the value for this y dash is positive. Alright? Okay. So here is for this one. Let's try to have a look at another one. Y equal to x to the power of 3. So y dash will become 3 times x to the power of 2. Okay? Bring the power to the front. This power will be minus 1. Become 3 times x to the power of 2. Okay? Maybe x. This one. X cubed. So this one would be y equal to x to the power of 3. Okay, so this one will be a keep increasing function. The y dash 3 times x cubed would be a parabola function. So this one will be y dash equal to 3x squared. Okay? Wait, let's try to find the relationship between the original function and its derivative function. The original function is the increasing function at all the value of x. It's all increasing. Right? For the y dash, it's all positive. All positive for all the value of x. Let's try to summarize the pattern from these two graphs. The first one is when the derivative function is negative, the original function is a decreasing function. So when the derivative function is negative, the original function is a decreasing function. When the derivative function is positive, the original function is an increasing function. Okay, we are having two situations over here. What about the y dash equal to 0? What can we have for y dash equal to 0 of the original function? When y dash equal to 0 is at this point. At this point. As I said, the derivative function is the gradient function of the original function. Y dash equal to 0 means the gradient is 0 of the function at the specific point. So here will be at x equal to 0. At x equal to 0. It doesn't have to be x equal to 0, depends on the question. Okay? So here, when x equal to 0, we can have a minimum point of the original function y equal to x squared. Right? But here, this point is not a minimum nor a maximum of the original function y equal to x cubed. But the gradient of the function at this point is 0, which means here the function is keep increasing, but it's get flat over here. So at this point, the gradient is 0, it's flat. It's flat. And then turning up, keep increasing of the function. So this point we call stationary point. Also, we can call this point as a stationary point, which means if we can have a y dash at x equal to specific x equal to 0, then this point is a stationary point. Okay, we can using this one to find a maximum or minimum of a function in two situations. If a function increasing over here and then decreasing, then we can find a maximum point over here, a maximum. At this point, its derivative would be equal to 0 at this point, at this x. Okay? Another situation is, okay, the function is decreasing over here and then increasing over here. Then we can find a minimum over here. At this point, is the derivative also equal to 0. So here, the derivative function is positive. So from positive to become 0 to negative. For example, here, this one would be this one. So from negative to 0 to positive. So from negative to 0 to positive. Then we can find a minimum of the function from here, right? If the function is, for example, y equal to negative x squared, then y dash would be equal to negative, we keep the negative side, negative 2 to the power of x. Then the function will look like this, right? Since the gradient of this function is negative 2, will look like this. So here is positive, here is negative for the y dash. And so here's the y dash. So here would be when the y dash is positive, the original function is increasing. When the y dash is negative, the original function is decreasing. Then we can find the maximum over here in this situation. Okay? But this one is not. This one is from not positive to 0 to positive. Then we can't find a minimum or maximum from this point for this function. So only for these two situations, from positive to 0 to negative, or from negative to 0 to positive, then we can find the maximum or minimum of the function. Okay, let's have the summarize of this video. The first one would be finding the derivative of the function from the first principle of the limit of the function fx plus h minus fx divided by h when h goes to 0. Here's the first principle for us to find the derivative of function. Okay. Second point, from our 3 sample questions, we have found the formula for us to find the derivative of the function in the form of y equal to x to the power of n. Then y dash will become n times x to the power of n minus 1. Okay, so bring the power to the front, and then power minus 1. So it would be, this one would be the derivative function of this original function. Okay, this formula only works in this form. Okay, I'll tell you much more in the later, but this formula is only for this one, only for the form x to the power of n. Okay, okay, this the last one. When y dash is positive, then the original function is an increasing function. Okay, so it will be an increasing function. When y dash is less than 0, the original function is a decreasing function. Oh. Decreasing function. When y dash equal to 0, we are having a stationary point. Okay? In 2 situations, we can find the minimum or maximum of the function. Okay, in 4. If the function starting from increasing and then decreasing. So positive means the differentiation of the function. The differentiation is positive, so y is negative. Here, then we can get a maximum of the function. Okay? Another situation is if the function is starting from decreasing and then increasing. We can have a minimum of the function. Okay? So here is 2 situations for us to using the stationary point to find the maximum or minimum. Depends on the question. Okay? Yes, that'll be all for this video about finding the derivative from first principles. In the next video, I'll show you how to do the calculations with derivative. Hopefully my videos could help you to have a much better understanding about high school mathematics. If you like my videos, please give me a like and subscribe my YouTube channel over here. I'll see you in the next video.